Hi, I'm Nayon with Scientific Analog. For the next 40 minutes, I'd like to give you an introduction to our products and brief demo. We currently offer three products: X Model, Glister, and Model Zen. I will start with a quick overview on what each of these products is. X Model is basically a plug-in extension to System Verilog, enabling fast and accurate analog mixed signal simulation in System Verilog. X model has a unique event-driven algorithm that delivers 10 to 100 times faster speed compared to competing solution called real number Verilog. In addition, X model runs analog simulation not only with functional models but also with circuit-level models. With X model, you can verify your chips that have both digital and analog parts within system Verilog, for example, using UVM. Glister lets you build top-down models in a schematic form within Cadence Virtuoso. With Glister, you can express your top-down models simply by placing the X model primitives on a schematic and connect them using wires. You don't need to write any code. Glister can then list out the system Verilog codes from your schematic. On the other hand, ModelZen is a bottom-up modeling tool. It can automatically extract or generate a model from the circuit, either in a schematic or netlist form. By default, ModelZen extracts circuit-level models without requiring any inputs from the user. And with a little guidance from the user, ModelZen can also extract functional models. For both kinds of models, the model parameters are calibrated via SPICE simulation, and the generated models simulate fast and accurate thanks to the event-driven algorithm of XModel. This slide gives an overview of the verification flow using XModel, Glister, and ModelZen. First, you need a set of system Verilog models describing your system. Your system may have digital parts as well as the analog parts. Glister and ModelZen can help you develop the analog models in your system. For a top-down model, you can describe it in a schematic form using Glister, and for a bottom-up model, you can extract the model from the existing circuit using ModelZen. Once you have the models, XModel lets you run efficient simulation with these analog models in System Verilog and deliver results such as waveforms or logs. XModel has a unique event-driven algorithm that delivers both fast speed and high accuracy by triggering a few events during the simulation. So I will demonstrate this with a small example. This example models a very simple high-speed I/O transceiver. A random digital signal is converted to an analog signal, which then propagates through a lossy channel. This filter then tries to recover the original waveform. Let's run the simulation with XModel by clicking this play button. Then I will plot the waveform using XWave, our waveform viewer. I am plotting the signals. And you can see that signals after the channel and filter are smooth and continuous. However, these markers indicate where the events are triggered during the simulation, which are very few. Basically, each event on the signal is triggered only when an event at the corresponding input occurs. This is why we call our algorithm an event-driven algorithm, and this is why XModel is so fast. Let me give you a bit more detail. Most analog simulators such as SPICE and real number Verilog use a set of points to describe the analog waveform. But with this approach, to get a high accuracy, you need a lot of points. But to compute such a lot of points, you need to sacrifice speed. XModel adopts a completely different approach, describing the waveform with a functional expression. Using this expression, XModel describes a waveform that varies over time just with a single event. And it triggers a new event only when this functional expression has to change. Turns out, this functional expression can be easily translated into a Laplace domain. Once you have your input in Laplace domain, and you also have a Laplace domain transfer function of your system or circuit, you can compute the output response in Laplace domain simply as a product between the two. This computation is fully algebraic without involving iterations. Also, this computation needs to be done only once when the input expression is updated. It enables a true event-driven simulation. We often make this analogy with the vector fonts. XModel is like a vector fonts that achieves the best accuracy and speed regardless of the time steps. On the other hand, other simulators such as SPICE, Verilog AMS, and real number Verilog are kind of like bitmap fonts that rely on a set of points. Let me demonstrate the speed and accuracy of XModel using a high-speed I/O link example. The example link includes a phase-locked loop that generates a transmitter clock and data recovery that recovers the clock for the receiver, and various equalizers such as transmitter side equalizer and receiver side equalizers, CTLE and DFE. These are the simulated waveforms at different points on the system. The transmitted signal is a discrete signal, but turns into a continuous signal after the channel, CTLE, and so on. But the number of events on each waveform is the same with that on the transmitted signal. This is thanks to the event-driven algorithm of XModel. By overlapping the waveforms on a bit-time basis, you can construct the eye diagrams and see that the equalizers do recover the loss of the channel. In XModel, the speed is virtually independent of the time step thanks to the event-driven algorithm. In system Verilog, time step is basic unit to describe the time of the simulation. Even when you reduce the time step 1,000 times from 10 picoseconds down to 10 femtoseconds, the number of events during the simulation remains the same and the runtime increases only by 10%. Nonetheless, XModel does not sacrifice any accuracy to achieve this fast speed. The use of functional expression allows XModel to deliver exactly the same results between the time steps of 10 picoseconds and 10 femtoseconds. For this example, we wrote the equivalent model in Verilog A and compared the results. We found that for the error bound listed here, XModel was 45 times faster than Verilog A. Well, most people don't use Verilog A for system level verification because Verilog A is based on the SPICE. Most actually prefer a system Verilog based solution. Real number Verilog is one of them. Let me give you a brief idea on what real number Verilog is. Real number Verilog basically uses this real-time feature from system Verilog that allows you to pass analog signals across the port boundary. But that's pretty much it. Users have all the burden of describing what the circuit does in Verilog. What you typically end up doing is describing your analog circuit as a discrete time filter, updating its output at each time step. But with XModel, you don't need to write code yourself. Instead, you just put together the basic blocks we call primitives to describe what the circuit does. And the resulting model will run fast in an event-driven fashion. Here are the simulated waveforms of the PLL's locking transients. The real number Verilog model produces different results depending on the time step. Particularly, if the time step is too coarse, the PLL may not even reach a correct lock. On the other hand, XModel produces the same accurate results no matter which time step is used. Here are the jitter histograms measured using the two models with different time steps. In real number Verilog, the time step has to be at least 0.1 picoseconds to get a reasonable jitter histogram. XModel always gives the best looking histogram regardless of the time step. Here is the comparison on the simulation speeds between real number Verilog and XModel. The speed with real number Verilog gets proportionally slower as the time step gets finer. On the other hand, the XModel speed is independent of the time step. Let's talk a bit about writing models in XModel. We made a lot of efforts to make analog modeling easy and fun. First, we offer a rich set of primitives. You can describe your analog models just by putting together these XModel primitives. It means you don't need to be an expert in all the language features of system Verilog. Currently, we have 7 different categories of XModel primitives. First one is called domain translators, which convert between a clock and its properties such as delay, duty cycle, period, phase, and frequency. The next is called stimulus generators, which generate various analog and digital signals used in your test bench that drive your model. We also offer digital gate primitives with XBit type inputs and outputs. These are useful when describing digital gates that process pulse width or timing of the signals. The next is connect primitives, which convert the signal types, for example, between the analog exterior and digital XBit. Also, we have measurement primitives that can make various kinds of measurements on the signals during the simulation. These are useful when writing assertion checks. Not only that, XModel has circuit primitives to support circuit-level simulation within system Verilog. Last but not least, these function primitives describe the functionality of the analog circuit, such as filtering, integrating, nonlinear functions, conversion between analog and digital, sampling, delaying, and so on. In total, XModel currently offers more than 150 primitives. There are two kinds of models people write for analog circuits. We call them block level model and circuit level model. The more technical terms are signal flow model and conservative system model, respectively. For the block level model, you can describe the system as a set of blocks in which the signals flow in one direction only. Each block takes an input and produces the output based on the input. On the other hand, circuit level model describes an analog circuit using a set of voltage and currents, and these voltage and currents are determined simultaneously by the governing circuit equations. XModel supports both block level and circuit level modeling in system Verilog. Basically, if you describe a circuit using function primitives, it becomes a block level model. If you use the circuit primitives, it becomes a circuit-level models. The circuit-level modeling of X model is useful when there is a circuit that cannot be easily described as a block-level model. For example, it may be tricky to describe this switched capacitor converter. In X model, you can just describe this circuit as a set of 4 switches and 2 capacitors using the circuit primitives. Nonetheless, the simulation of this model does not require SPICE and runs entirely within system Verilog in an event-driven way. These circuit primitives are also useful when modeling various nonlinearities of the analog circuits. For example, the gain of this differential amplifier may get compressed when the input signal becomes too large. Knowing that the transistors and diodes are the source of all nonlinearities, modeling the circuit simply with circuit primitives guarantees that the model would contain nonlinearities. This table compares X model, real number Verilog, and Verilog A. First, Verilog A is based on SPICE, therefore it can model anything analog. But because it is based on SPICE, it is typically very slow and not preferable for system Verilog-based verification flows like UVM. Real number Verilog tries to model analog in system Verilog, but many of the models users end up writing perform fixed time-step simulation, updating outputs every time step. Therefore, the speed and accuracy of the simulation can heavily depend on the choice of the time step. Also, since System Verilog is basically a signal flow modeling language, real number Verilog has limitations in simulating circuit-level models while also requiring some special language features to do so. On the other hand, X model is entirely based on System Verilog, but thanks to its event-driven algorithm, it is both fast and accurate regardless of the time step. Also, the rich set of X model primitives support both functional and circuit-level modeling and make the modeling of analog circuits very easy. Now, let's switch our topic into the flow of writing models. There are largely 2 approaches, top-down and bottom-up modeling. Top-down modeling is a process of describing your ideas into models, so you can check whether your ideas work before building the circuits. For example, you can explore different architectures and then choose one of them to implement as circuits. On the other hand, bottom-up modeling is a process of extracting models from the implemented circuits. Then you use these models to run efficient top-level verification. Glister and ModelZen are the right tools for the top-down and bottom-up modeling flows, respectively. With Glister, you can compose top-down analog model in schematic forms and then list the system Verilog models. With ModelZen, you can auto-extract bottom-up models from the existing circuit. Let's look at Glister first. Glister is a graphical interface enabling you to use XModel and ModelZen within Cadence Virtuoso. For instance, you can compose models in schematic forms, run XModel simulation, and auto-generate models using ModelZen. Glister offers all the XModel primitives as symbols, and you can easily compose a model just by placing these symbols on a schematic and connecting them with wires. Each primitive symbol has a built-in documentation view, so you can read its description simply by opening the doc view from the library manager. You can also launch XModel simulations with Virtuoso. For example, using XModel Test Bench Editor, you can easily configure a test bench and run simulation. Now, Let's look at the bottom-up modeling. When you want to extract a model from the existing circuit, there are largely two approaches: structural modeling and functional modeling. The first approach is called structural modeling. First, model the individual components that make your circuit. Then, build a model by connecting the component models using the same topology as in the original circuit. The advantage with this approach is that it can be easily automated while guaranteeing correct by construction models. The second approach is called functional modeling. First, you choose a template model that best describes the functionality of your circuit. For example, a linear filter followed by a nonlinear function. Then, you calibrate the parameters of the model that reflect the actual characteristics of the circuit, such as the gain and pole and zero frequencies. Again, ModelZen is a tool that can automatically generate bottom-up models from the circuit schematics or netlists, and it can support both structural modeling and functional modeling. Glister provides a nice interface to ModelZen in Cadence Virtuoso so that you can generate a model from a circuit schematic with a single mouse click. In Glister, you can select this menu called Run ModelZen or click this icon to extract a model from any circuit. Glister will perform all the steps necessary, such as extracting the SPICE netlist, running ModelZen, and generating models, and then importing them back into the Cadence database. Seeing is believing, so I will give you a quick demo using a two-stage op-amp example. This is a schematic of a two-stage op-amp composed using the analog leaf components. So you can pretend that this is your schematic composed with the foundry PDK. Like I said, extracting a model with ModelZen requires just a mouse click. Click this Run ModelZen icon, and ModelZen first extracts the SPICE netlist from the schematic and open this dialog window asking for your confirmation. When you click OK, the model generation process begins. ModelZen characterizes the individual elements contained in the circuit and builds a structural model using the XModel primitives. The generated model gets imported back into the Cadence database into a view named XModel. So from this model, you can see the transistors, diodes, and capacitors in the circuit are listed in system Verilog syntax using the corresponding XModel primitives. Let's try to run the simulation with XModel. Here is test bands that feeds a small sinusoidal input to an open loop op-amp. I can run the simulation by clicking this play button. When the simulation is completed, and open the waveform viewer by clicking this wave button. From the waveforms, you can see this op-amp responds with a large swing even when the input signal has a very small swing. Also, the output is clipped by VDD and VSS, indicating that the generated model can properly model nonlinear effects. On the other hand, Let's see what happens when you put the same op-amp model into a resistive feedback loop. Here, I generate the model and run the simulation. Now you see that the circuit produces a linear response. That is, for a sinusoidal input, the circuit produces a sinusoidal output, where the gain between the input and output is set by the ratio of the two resistors, which is -10. Structural modeling is nice as it guarantees correct by construction models, but the speed up achievable may be limited since the resulting model is not any simpler than the original circuit. ModalZen now has a new interface called User-Defined Model or UDM interface, which can generate higher abstraction models, including functional models for any selected parts of the circuits. For example, you can map this part of the circuit to a voltage reference UDM and this part of the circuit to an amplifier UDM. Then, ModalZen generates a functional models for those parts based on the user-defined templates. Often, these functional models run much faster than the structural models. Here is the example of voltage-controlled oscillator used in a phase-locked loop. The structural model for this VCO may run slow because it constantly generates a lot of events during the simulation. Instead, we can select this VCO circuit and map the VCO to a VCO UDM. Then, ModalZen generates a functional model for this VCO. You see that this VCO is modeled using piecewise linear function primitives that maps the input voltage to a frequency and the frequency to clock primitives that generates a clock with that frequency. And these numbers describe the voltage to frequency characteristics of the VCO, which are characterized by the sparse simulations run by ModalZen. Using UDMs requires users' inputs, but good news is that you don't have to use UDMs for each and every part of your circuit. You only need to do so for a few critical blocks. In this PLL example, we found that modeling just the VCO and divider as functional models could achieve a 17x speedup compared to using all structural models. In summary, XModel is a fast analog mixed signal simulator that works seamlessly with the existing digital verification flows such as System Verilog and UVM. Compared to real number Verilog, the XModel's event-driven algorithm delivers both the fast speed and high accuracy, and XModel supports both block and circuit level models. And Glister and ModalZen are modeling tools that help you either compose top-down models or generate bottom-up models for your analog circuits. As a system-level example, I'd like to demonstrate a top-down and bottom-up modeling of a DC spot regulator. Here is a top cell of the DC spot regulator model composed in Glister. This regulator is made of a buck converter stage producing the output voltage and a PWM controller monitoring and regulating the output. The buck converter stage is made of two power switches and inductor and capacitor filter driving on output load resistance. All these symbols are the X-model circuit primitives. The gate driver cell is modeled as a set of logic gate primitives to produce non-overlapping pulses. This part that switches a capacitor between a power and ground models the dynamic power of this gate driver. The controller is made of PID control filter and pulse width modulator. The PID control filter is modeled using function primitives such as integrate, scale, derivative, and add primitives, and monitors the error between the Vout and Vref and produces a proper input to the pulse width modulator. The pulse width modulator is modeled using the two primitives, limit and duty to clock primitives, to modulate the duty cycle of the output pulse based on the input. Now, let's try to run a simulation with these models. Here is a test bench. The test bench feeds an input voltage of 5 volts and the reference voltage of 2.5 volts. And open the test bench editor and click this play button to run the simulation. Once the simulation is done, and click this wave button to open X-Wave. You can see that the DC regulator output settles to a 2.5 volt as expected. And when you zoom in, you can see the ripples on Vout waveform. Next, let me demonstrate a bottom-up modeling of a DC regulator using Model Z. This is a circuit schematic of this buck regulator. It may look almost the same as the previous example, but all the leaf cells are described in transistor level using the analog leaf components. For example, here is the buck converter stage. Here is gate driver. And here is the circuit implementation for the PID controller and the pulse width modulator. Generating the bottom-up models is easy. Just click this Run Models and icon at top level. By default, Models N generates structural models for each cell in the hierarchy and imports the model in the X-model view. Here is the generated model. The model describes the circuits using the equivalent transistor or other circuit primitives of X model. And you can also map a certain part of this circuit to a UDM. Let's try to do that for the pulse width modulator. You go into the PWM cell and select the instance that make the PWM. Then select the pop-up menu, Models and Properties, or you can just press Ctrl Q. In this dialog, Select the model PWM_V1 and define the mapping between the nets on the schematic and birds on the model. Press OK and save. Now you can go back to the top level and regenerate the models by clicking the Run Mozarten icon. Let's see what we have got this time. This is newly generated model, which models the PWM using a UDM. This is described with a piecewise linear function primitives followed by additive to clock primitives. Okay, let's run the simulation with this model. Test bench is almost the same except it is a 1.2 volt of input and a 0.6 volt reference. Let's check the waveform. As we expected, this converter model produces a 0.6 volt output, and the output has ripples due to switching action. That's it, and I would like to conclude my webinar. I hope that this webinar gave you a good idea on what X-model, Regulator, and Model can do for you. Please visit our website or contact us if you have any questions. Thank you.